In this example, we want to show that the rate of change of f of x in the direction of a unit vector u, which is called the directional derivative and is denoted du, has maximum value given by the gradient of f and occurs in the direction of the gradient. Okay, so we define the rate of change of f in the direction of a unit vector u as the directional derivative d sub u. D sub u is equal to the dot product of the gradient and a unit vector. The maximum value of du is, we want to prove, is the length of that vector and is in the direction of the gradient. So let's prove this. So we're going to let the gradient of f be fx, fy, fz. And we're going to let u be a vector a, b, c. Then du of f is, we've defined it to be fx, fy, fz, the gradient of f, dotted with a unit vector a, b, c. Right, we should note here that length of u is 1. Now, if we think about our rules of dot products, we know that cosine theta is u dot v over length of u, length of v. And because we know that, we can solve for the u dot v, which makes this equal to length of the gradient times length of our unit vector u times cosine theta. We also know that the length of u is equal to 1. So at all times, this directional derivative is the length of the gradient times cosine theta. So to answer the questions here, what is the maximum length of du? Well, it's the length of the gradient times cosine theta, and cosine theta is maximized when cosine theta is equal to 1. So the maximum value is the length of the gradient. And how do we get there? Well, theta is equal to 0, right? Because cosine theta is equal to 1, so theta's got to be equal to 0, which means u and the gradient of f have angle 0, or parallel. So the maximum rate of change is in the direction of the gradient of f, right? So for at any particular point, or for any spot in space, the maximum rate of change is equal to the size of the gradient and is in the direction of that maximum gradient.